Now that we've got our system installed and we know how to get up booted, can deal with the init.d scripts, deal with EFI, also go to rescue mode if we need. We've also built file systems. We're now basically ready to use the system. Seems no sense to me to be an administrator and not be able to run some basic applications or put some sort of stress test on the system before you hand it back to the users. So in this module, we want to talk about the module command. Now the module command originally came from Sun Solaris. Cray had implemented it, and then when Cray and SGI merged, it was put into IRIX, and then it was put into Linux. But there are Red Hat and SLES flavors as well, and they are different. The one that SGI uses, I believe, is the SLES version, not the Red Hat version. They have different names to the RPMs, and they have different paths. You got to watch for Red Hat versus SLES here. And there is a directory here with a .modules path in it that says, where do I find module files? Now, module files basically modify environment variables. The module command is an alias built into the shell that can change your path, your library path, your man path, things of that sort. So the module command can show me what my current products are, list available products, and then load and modify my path so that I don't need Photoshop in my path unless I'm using Photoshop. In fact, this is one thing that I like of Linux over Windows. I hate the registry in Windows and put all your problems into one file. And I'd rather have module files than have dot files when somebody logs in to do the creation of the environment variables and to set up what you need for that application. At least the module file is not in your environment unless you need it. And if an administrator moves or changes a product, they change one module file, and then all users are picked up with the change rather than having users changing their dot files to do something. Also, you're going to install the Intel compilers. And the other piece here is to get array services working, which is part of MPT. Now, tomorrow, I want to go multi-partition MPT and run MPT across all nodes. So I've kind of got a busy plan for tomorrow because I want to do an XVM demo, and I want to finish up with the MPT demo. There's a command called arrayconfig that can configure your array services, particularly in a cluster, whether it's a flat cluster or an ice cluster. And then there's an ascheck to make sure that array D is talking across the cluster. There are some other commands I don't really care about. Nobody really uses these commands anymore. Instead, the C3 commands like cexec, cpush, cget, or the pdsh commands are more commonly used as more publicly aware or publicly known cluster commands that will run a command across the cluster. Now, in order to use SGI's MPT, we got to load the module MPT, and then we're going to run it with MPIrun. Now, there is a command called Perfboost that can run other MPIs and use SGI's MPT instead. It's a Trojan library that will intercept, for example, Intel MPI library calls, and then call the SGI MPT version of that library rather than the Intel version. There's also a set of libraries called SGI Optimize. This kind of I don't want to say replaces, but is similar in intent as the older Cray SCSL libraries. Some unique routines that have been optimized. Also starting to be used, particularly in a batch environment, is the checkpoint facility. It's called the Berkeley Linux Checkpoint Restart. This allows an application to save off its state in a file. And then if we take a shutdown and a service interruption, we can pick up from that checkpoint file. Also, there are UV statistics available. I don't know how much time we'll have with them. I've been kind of running behind here with some of my demos, but that is something I get into in the next class, the Unix System Analysis class. I'm going to leave that for tomorrow right now. So the module command provides a dynamic modification of my environment through these module files. Each module file is for a unique product, for a unique application. User's environment can dynamically modify using the module command. This centralizes the paths and the location of the products to the administrator, and then you don't have 50 different users that have to change their scripts or their doc files to be able to find the product. So these module files are shared by many users. Internally within SGI's benchmark center and stuff, we use the module command all the time to get to compilers and different versions of compilers and different versions of MPI, OpenMP, and other applications that we need. So you have a package called modules. On Red Hat, it's called modules environment lowercase. They are spelled differently. It's a user share modules. What did I have here? Yeah, I'm just checking. On Red Hat, it's an uppercase M instead of a lowercase m. Documentation and user share doc packages. And basically, when you log in, there's an itcprofile.d modules.sh or .csh that invokes a shell that understands the module command, that the module command is an alias or a function built into the shell. You cannot have the module command a child process. If I fork off a child run module, it can't pass those environment variable changes back to the parent. You can't export these changes back to the parent. So that's why it's an alias built into the shell. Now, if I come in through batch like PBS, Torque, LSF, or if I come in through the VNC remote desktop, or even if I SU, I might pick up a shell that is not aware of the module command, in which case I normally source itcprofile.d modules.sh or CSH. Now you add your local modules. Here they're adding it in the user share module files, but that has a problem because SUSE will overwrite them. So what we generally do is a /SW instead of /opt. I had one site calling it /software. The older convention was to use /opt, but now SLES and Red Hat put things into /opt that are synchronized and tightly bundled to the distribution. /SW is for the asynchronous, unbundled, loosely coupled applications like total view and compilers and things that are not part of the distribution. So rather than trying to keep the two synchronized, we've just created a new naming convention here for our asynchronous, unbundled products that are usually exported to the entire data center. So here's a module file example. These module files are written in Tickle, TCL. So this module file, the set command is basically setting a variable called manprev. The brackets are saying do a substitution, and the execute is executing the man path, throwing away any errors, and then substituting that so that manprev will be set to what the prior man path was. Then they're setting the new man path to what this prior man path was, and then they're appending, or I should say prepending to it in front of it, opt SGI man. That's a way of picking up the older man path and then adding to it. That's kind of a workaround that's always been a problem with the module command, is if I just did prepend man path, it didn't know what man path was. I'm also adding to the path opt SGI Perfboost bin, and now adding to the library path, load library path, opt SGI Perfboost lib. So that's a simple example. Now in lab, you're going to create a module file for the Intel compilers after you install them. So the module command is a user command to change my environment variables. It allows me to switch between different module files. I can load and unload. I can switch to different compilers, switch to different libraries. The most common environment variables are path, load library path, and man path. But maybe Photoshop needs a Photoshop underscore environment variable. So depending upon the product, they might have additional environment variables that are unique to that product. There's a profiling tool that SGI runs called Perfsuite from NCSA in Champaign, Illinois, the National Center for Supercomputer Applications. And Perfsuite has a PS run command that can profile subroutines within your application that you're spending all your time. And that per suite has additional environment variables that you could put into your module file rather than the default Linux ones. So here I did a module list showing that I currently have an MPT 2.8 module file loaded. They did a module avail, and then I can see user share module files and the ones that came with the distribution. Now, if there's nothing there, by the way, I'm going to put it in here. You can also do a module use /sw/swcom/module files, for example. Typically, within our data centers, we have a /sw that might be available, but it's not in the path for the module command to look for. So you can say use that directory wherever your files are. Remember, this directory gets stepped on if I reinstall my golden root. This one would not if it's on a different partition. So module avail will show the modules I can pick up. They did a module load, and they listed it and showed that it got loaded. And then you can actually do a module show to show what the module did, what environment variables it changed. Moving on, we have array services. Array services is unique to MPI. It is a way of running an MPI application across a group of hosts. Each host has its own host name. And by the way, the word node is sometimes misused. So in PBS would call each of the hosts a node, versus Linux that calls a node a socket and the memory attached to that socket. The array services gives greater performance for applications, lower latency startup. Original MPIs would have to open up a port on the remote host, invoke XINetD or something like that. That would then invoke something like RSHD. Then you'd get the shell, and all that stuff took time. The array D is up and running all the time, ready to listen and spawn work much more quickly. It's used by SGI's MPI. We call it MPT, Message Passing Toolkit, because it contains more than MPI. It contains another library called Shemem that came from Cray and was ported into IRIX and then in Linux. And it used to have some other things in it like Arena and PVM and some other applications. So MPI is a standard library interface to distribute an application across multiple hosts. It could be on the same machine using shared memory. It could be using NumoLink between 100 racks of UV. It could be using InfiniBand on a flat XE or an ICE cluster, or really, really cheap. We're not using it, but MPI can also just be using TCP. So array services, by the way, I thought I fixed this. The SArray services RPM is gone. That's being replaced. They're just going to be using something called Munge. So rather than having two flavors, the standard one is not encrypting the network socket traffic. The secure version was encrypting it, but now they're going to be using Munge instead of having two versions of it. And again, that secure array services is gone in the release that you've got installed. It wasn't there that I saw. So you need actually three RPMs, SGI Proxet, SGI Array Services, and SGI MPT. The Array D daemon is what communicates between the nodes. And I'm going to save this for tomorrow and run an MPI application across all four nodes. I want to do it after I've got PCP going. Machines in the cluster are defined in this arrayd.conf, and authentication, whether you want authentication or not, is specified in arrayd.auth. By default, it says no remote connections allowed. There's an array config to configure this. You'll do that in lab. Make sure the array's on and started, and also with Proxet. So this array D communicates between the hosts in the cluster. It assigns something called an array session handle for any work spawned across the cluster. It can run commands across the cluster, but again, most people are not using that. They're usually using something like cexec or pdsh. And both of those are in our ICE distribution by default. It maintains some files about the array configuration, determines which processes belong to an ash. So here's the thing, if I have a particular node in my cluster that goes down, with array services, it's going to check that a MPI job died on one of these things, find all the processes associated with that job, and then kill it across the cluster. Also, ArrayD is using var run array services. There's a network socket connection, and you might find error logs in there, but I always check var log messages too. So here, if I'm running an application, MPIrun, or there's a library, a libarray API to it, or some basic commands, they'll talk to ArrayD, and the ArrayD can talk to the local daemons and run processes on the local system, or talk to a remote ArrayD, which will then spawn off remote threads or ranks of an MPI application. So array services is using these commands. Frankly, the last two are the only ones relevant. Nobody really, only in some cases would you need ainfo, but nobody really uses these commands. There is an array command, and it's using a call called array services as a default account to run commands across the cluster. So it did an ainfo to see my ashes or sessions, then did an ainfo on a session ID to figure out the PIDs, and then I did PS on the PIDs. Here we did array that can kill, run PS, resume, signal, things like that across the array. Again, most people are not using this. Instead, they're using either cexec or pdsh. Those are more common cluster array commands that were more well-known and popular to the cluster community. So here are array-who, uptime, PSs. So there's an arrayD.conf file, got 4 types of sections in it, the array definition, command definitions, authentication. So here I've got an arrayD.conf specifying array called Floyd. I've got 4 arrays, 4 hosts to it, and these are all going to use numalink to talk between them. But I've got to configure XPC. XPC has to be loaded. It has to be the same version of XPC on all the hosts within the numalink cluster. Also, when I submit to the cluster, I'm going to specify Floyd as the default cluster to submit to. Now, this can be built by arrayconfig. So it did an arrayconfig, name the array Floyd, make the arrayD.conf file, no authentication, copy the arrayD.conf file to all the nodes, and then list the nodes. And then did an ascheck to see that everything looked clean. So then I did an array-a Floyd uptime to see that everything was up. Now, to run an array command or a MPT command, I'm going to load MPT, and then I got to compile it, and then I'm going to run it with MPIrun. And again, ArrayD is with spawning the ranks. There is a command, I don't use cluster viz, but I do prefer PMG cluster quite a bit. I use that quite a bit. So here I've compiled the application, then I run it, or if I'm on a multi-host, this is only local, but here I specified the host that I want to run on. And that binary has to be in the same place on all the nodes. That's why we have a home directory that's NFS mounted on these Floyds, so that my executable will be visible in the same path on all the hosts within the cluster. Here is for PBS or LSF or torque. So they're compiling it, but then there is a wrapper called MPIexec MPT. This is going to make sure that end users can't break outside of the hosts that PBS has told them they can run across. So if I run MPIrun, I could still specify hosts that I was not legally able to run on. This is going to double check that and contain me to the host that PBS has told me that I can run on. And then we've got a multi-host run here, or we can put it in a machine file. One thing I don't like about this flavor of MPI, by the way, it's a comma-separated list, whereas all the other MPIs are a new line carriage return list, where every host is on a separate line, not a comma-separated line. So I have algorithms to convert the commas into a carriage return. There's also a profiling tool. I don't cover it here. This is part of the next class. But MPInside is an SGI profiling tool. They loaded MPT, loaded MPInside, compiled the application. Then when they ran it, they ran MPInside right here. And then it can give me statistics about how much time I was starting my threads, sending data, waiting to receive data, or synchronizing on a barrier. Now, barrier synchronization is a common problem out there. The way I like to describe barrier synchronization is like playing phone tag between my threads. A barrier is a synchronization point in my program where I say, is everybody done with your calculation? I can't go on to my next iterative do loop unless you're done with this particular loop. So when I have a barrier that sticks, that's where my threads are actually playing like phone tag between each other. And the thread sitting there saying, are you done? Are you done? Are you done? Are you done? And that other thread never calls me back to tell me that they're done. So we're timing how much time we're spending in the barrier. And then it's giving other data like megabytes transferred, number of requests across the interconnect. Here's Perfboost using SGI's MPT, but was not compiled with it. It's a wrapper library that will run other MPIs and then call SGI's MPT. Have to be a recent version. There's a user module. So basically you do MPIrun, and then this, by the way, is the number of ranks or threads you're going to spawn off. And then here we're going to do a Perfboost and specify that this is the Intel MPI. So it's going to convert the Intel MPI library calls, intercept them by that Trojan library, and then call SGI's MPT instead. There's also Checkpoint Restart as part of the SGI MPI distribution. It is its own RPM. This enables MPT jobs to be checkpointed and restarted after a system restart. And a reboot would have occurred in here. So it pauses MPI communication, brings it to a controlled idle where it's safe to do checkpoints. We can't checkpoint applications that have open sockets across the cluster and stuff like that. So this is supporting these types of interconnects for us. I don't want to get into this too much right now. This is a UV hub. On UV2, it's actually two of these, what they call a hemisphere 0 and a hemisphere 1. We have four sides, if you want to call it that, to this processor, the chip. This has been called a hub, a shub, a bedrock, a harp on the UV2. The first interface is off to the quick path interconnect. So this is going off to Intel protocol. Notice I got two QPI ports coming out of here. From there, we're going into what's called local home and remote home. This is for cache coherency. And local home is where the directory memory is attached to keep track of things. I still have to check on this. I don't have a drawing of this for the harp in UV2. So UV2 is slightly different in this area. Remote home is the one that sends my invalidates to remote memory when a locally cached file, a locally L1, L2, L3 cached memory line has been written or modified by the processor, and every other CPU that has a copy of it has to go to directory memory, get a bit mask, and then every CPU that's got a copy of it is going to get an intervention and an invalidate sent to it through Numolink to tell it that that line is invalid. So local home and remote home are for cache coherency CC NUMA events, dealing with what's called false cache sharing. And when you have an application that has what's called a hot cache line, where everybody's writing to the same cache line, the information coming out of these can be useful to find where in your program the hot cache line is. Now, another thing coming out of this processor is the NumaLink ports themselves. So I got 4 here. With the latest one, it's 8 ports per hemisphere, 2 hemispheres within the chip. So you got 16 NumaLink ports coming off of a UV2 heart chip. Also in here are 2 block transfer engines called the GRU. This is for a memory-to-memory transfer. Lastly, we have the programming API to the hub or the heart. This is what UV dump gets its data from. This is where we get diagnostics. This is where we get statistics for linkstat. There are a variety of things that are going on in here, including something called the MPI offload engine. This is a way to barrier synchronize and use the hub hardware support to interrupt another processor and say, I'm talking to you, would you listen to me? This is to reduce the latency in barrier synchronization rather than going through memory in a polling type of mechanism. So there is a linkstat command, again, I was looking at earlier. I don't want hide. One of my tuning objectives would be reduce my interconnect traffic. Just because it's there doesn't mean I want to abuse it. A system can get very, very busy and get very sluggish if the interconnect is busy. And if you have a large slab, that also is going to tie up your interconnect. And if you got migration going on, that's also going to tie up your interconnect. Now you can also get to other statistics. In this case, HubStats is getting to my local home and my remote home and my NumaLink traffic. And there's a linkstat-uv -A that needs to be done to start it. So I got to save this for tomorrow, but I've gotten into PCP here, and I'm running an MPI application here, and I can see the NumaLink traffic that's going on during this application. Let me save that for tomorrow. Also, when I run an MPI application, I can get statistics. For SGI's MPT, you do a -stats. And by the way, this command line is position sensitive. I've got to put miscellaneous arguments here, then my host list, then NP and a number, then the application. I can't put the host list earlier or NP earlier. It's basically MPI run, miscellaneous arguments, host list, -MP, and then the application. So with -stats, I can actually see what's going on, and in particular, see how much the GRU is being used. So I can see that the global reference unit is being used as a memory-to-memory block transfer engine here. Now that could be good or that could be bad. So you can turn off the GRU. That is an MPT, MPI_GRU type of environment variable to turn it off. And that's it. Basically, in lab, I want you to install the Intel compilers, set up a module file for it. There is a template module file in the lab tarball. It was in /archive. Send me email if you can't find one. You'll also find stuff in /guest UVSA1. And then use the module command. Configure the module file path for the Intel compilers. Then I want you to check for SGI software. Configure array services. Now the lab's going to have you do it by hand with VI, and then you're going to use arrayconfig. So you're going to do it twice. And then do an MPI application. I am going to do this tomorrow. You won't be able to run across all partitions without sorting things out. So right now, do not do group multi-partition MPI. That's got to be a demo. I intend to do that tomorrow. I don't think we really have an application to run under Perfboost. I don't think I really care about profiling with MPInside. And then I'm going to do these last two as well. So basically, you're not going to do everything here.